Good morning, dear ladies and gentlemen. My name is Ivan Kolesnikov, and today I'll be presenting problem metallic forest. So the problem statement is the following. In the electrolysis of aqueous solutions of metal salts, fractal-like dendrites can begin to grow on the electrodes, and we should determine how does the shape and fractal dimension of these dendrites depend on setup parameters. So here you can see the overview of the report, and I'm starting with the introduction to my experimental step, which consists of a piece of glass, which was covered with two pieces of silver foil with a thickness about 20 microns, with a silver nitrate solution in between. And then it was also covered with another piece of glass to form a sandwich-like structure shown on the left. Then foil was connected to the power supply through the voltmeter and ampermeter to track the voltage and current in the system. Then the slide was placed into the microscope, and the camera was attached to the laptop. So we were able to track the structure of the dendrites during the growth process. What happens here is basically just a reduction reaction. So because of dissociation of silver nitrate, we have some concentration of silver ions in our solution. So because of diffusion and migration, there is some motion, and if the ion collides with a deposit or a cathode, there appears some reduction reaction. So our ion turns just into silver. To prepare my silver nitrate solution, I used chemically pure silver nitrate crystals, distilled water to prevent metal salts from tap water from corrupting my electrodes. And the whole solution was acidified with a bit of nitric acid to prevent anode from oxidation. So what is the fractal dimension which was asked in the problem statement? So by Minkowski, fractal dimension is a limit of the ratio of logarithm of the amount of cubes covering a given set to the logarithm of inverse size of such a cube. So how do we determine it for our non-infinite set? For example, given by our picture. What I do is conduct some image processing. So firstly, I cut my image to reduce the areas I'm not interested in. Then I filter it and apply a binarization algorithm to obtain the image on the right. Then I divide it into smaller and smaller squares to form, to build a double logarithmic plot shown on the right. What we can see here that there are some regions formed by such a pattern. So the first region is if the size of our subdivision is comparable with the width of the whole image, which doesn't bring much physical sense about the structure and dimension of the dendrites, so we don't include it. The next region is when the size of the cell is much larger than a branch size, which also don't bring much physical sense. However, there is also a region when it's comparable. So that's exactly the region we're interested in. And there is one more region when the subdivision is very small, but because there are some errors caused by the image processing, there is some noise. So we don't include these points because they bring much, they bring much error in it. And depending on how much points from the third region we take, we can determine 2-point method and 3-point method. That's how I determine fractal dimension for our images. Then moving on to a theoretical description, the process may be described by the transport equation with a diffusion term and migration term caused by the motion of charged ion. So we take an assumption that the rate of the deposition is much less than a mass transfer rate, so the concentration stays constant over our lattice. So we obtain quasi-stationary case. And also we should take into account that as our dendrite is conductive, we consider that the potential on the boundary of the dendrite is equal to 0. So we'll also be solving Laplace equation over our lattice, and here you can see how does the different ratio between the diffusion term and the migration term influence on the overall shape of the dendrite. You can see that the more is diffusion, the sparser our tree is, and the more is migration term, the more dense it is. Also, I should mention some qualitative notes. So because of the fact that our diffusion equation may be described as a Laplace equation in a stationary case, we know that the gradient to the normal near sharp edges is the largest. So I state that sharp edges will grow faster. And another fact which can be obtained from a Laplace equation is that there is some screening effect. So if there is a developed dendrite, the probability of a particle to penetrate deeply to the electrode is very small. So basically these two factors cause a fractal-like structure of the whole dendrite. And that's exactly what we can observe during the experiment. For example, on the right, you can see the video, and on the left, the final photo. What we can see is that we were right, and the tip of our electrode starts to grow faster. Also, there is a surface reaction process. Basically, what we have is a flux of ions to our surface, and there is only a rate of production. So not all the flux particles will become the deposit. So there is some reaction probability which is impossible to evaluate. So we'll consider it as a free parameter and find it later. What is our simulation is basically a Monte Carlo algorithm with some shifting probabilities which depend on the electric field at a given point. And the whole simulation process is the following. So we seed our grid with some initial particles, take some, and move it according to the algorithm. After the collision with the electrode, there is some probability of deposition, and it also causes surface relaxation, which is basically just the process of reducing the potential energy as the more neighbors the particle has, the lesser is the energy. So it may fall down during the whole after the collision. What I want to talk about now is the stability and convergence of the fractal dimension in my simulation. So what I did, I computed 7 simulations with a different grid size, and what you can see here is all of them approach the same value, and it leads us to the following conclusion, that the fractal dimension depends, which is approached by the simulation, depends only on given parameters, but not on the time and cell size, which is quite interesting that if we conduct the same experiment over and over again, the shape of the dendrite will be different. However, the fractal dimension will remain the same. Then I conducted a calibration experiment, as we have a free parameter in our system, and the overall shape strongly depends on this reaction probability, as you can see on the pictures on the right. I conducted more numerical experiments to determine the dependence of the fractal dimension to the reaction probability from a simulation. And by obtaining these two curves and obtaining the fractal dimension from the experiment, I was able to find the intersection of these two lines and determine the probability of the reaction for my simulation. Using which I can, for example, conduct the experiment of the dependence of fractal dimension to the applied voltage. What we can see here is that if the applied voltage is higher, the fractal dimension is higher, which is because of the higher migration term, because of higher migration term. And if the applied voltage is lower, the fractal dimension is lower because the transport is mostly caused by the diffusion, and the tree is more sparse, and so the fractal dimension is lesser. That's the conclusions, my references, and that's all.